A good application of the law of reflection we already talked about was mirrors. And now that we've talked about the law of refraction, or Snell's law, we're now ready to give it a good application, and we're going to do that using thin lenses. Now, a thin lens is a lens whose thickness is very small compared to their radius of curvature. So, for example, down here you see two types of lenses, the double convex and double concave. If I were to complete the circle for this lens, it probably looks something like that. That's not a circle, but yeah, that one might be a little bit better. We'll go with that one. So here's the radius of curvature. The thickness of the lens itself is very, very small compared to that radius of curvature. So you can have two types of lenses. You can have the convex lens and the concave lens, and different variations of each. And you can see here in figure C in the middle, here's an example of a convex lens, or a converging lens would be another name for it. And here is an example of a concave lens, or a diverging lens. And you can see on the right figure what each does. With the converging lens, you're going to have a handful of different possible images depending on where the object is located in comparison to the lens and the focal point. But with a diverging lens here, you're always going to have the same thing. You're going to have a small view of whatever it is that you are looking at. And we'll see that again when we talk in the next video, when we actually talk about calculations for thin lenses. Now, a converging lens is called that because when you have this shape of lens, which in this example is a convex lens on both sides, or a double convex lens, all the parallel light that hits the lens will then refract and pass through a single point on the far side. And that is what we call our focal point. With the diverging lens, on the other hand, any light that hits the lens will refract. So it comes in and it'll refract away. And so there's no way that that light will converge. So if your eye is over here, there's your eye, you see that light coming in, you're going to say, oh, that light's coming from this line, so that object must be over here. This light ray is coming from that line, so it must be over here, and so on. Whoop. Anyway, all of these light rays will converge at your focal point. Now, each lens is going to work a little bit differently based on the radius of curvature and the material. So in other words, the converging or diverging angles are going to be different. And so we measure the power or strength of a lens by this equation. The power of a lens is going to be 1 divided by the focal length. Now, don't confuse this power of a lens with power energy over time. It's not the same thing in this case. Power of a lens is just talking about how well does a lens refract. How much does it refract? The larger the power, you're going to have smaller focal lengths. Now, the power that we've talked about before is energy per unit time, or joules per second. The unit here would just be 1 over meters, or inverse meters, which we call a diopter. So that's a different unit for the power of a lens.